I would like to share a photo with you first. This picture shows a young father introducing a book to his two children. Why did he send this photo to me? Because he was very emotional and he said, I can now finally tell my children very profound earth science stories. This is my book published by China Geological Press recently. The Breakup of Earth, Earth Evolution as a Thermal System. I'm actually a geotechnical expert. My contribution is actually the study of rock fracture process and the analysis of engineering disasters. So why did I get involved with earth science? It's because of two accidental chances. 15 or 16 years ago, I went with my wife to the Coast National Geological Park in Golden Pebble Beach, Dalian. There is a treasure in this park called the turtle-like cracked rock. My wife asked me, you're doing the research of rock fracture analysis. How did this crack form? This question actually made me consider that I have to use a numerical simulation method. I went home and simulated the process of rock cracking. Look, the red diagram is a simulation of cracking. It is a very good reproduction of the process of a medium from the stress to the cracking, finally forming a complete cracking. In fact, this is where my fascination with cracking began. Not only that, but I've published a few good international papers, from small-scale rock cracking to the large-scale breakup of Earth. It was actually due to another chance. More than 10 years ago, I went to Nanjing Institute of Paleontology. Academician Shin Shuzhong gave me a beautiful photo. This photo is of a fossilized cell division from 600 million years ago. The cell division fossils is very, very small. Look, this is an image of a child playing with a mud pile, and it's dry and cracked. So these two images are almost the same geometrically. Of course, physically they are different, but the difference in scale between them is quite large. So this leads me to a question. On this scale, let me scale up. Let's look at this image on the top right corner, which is the Gondwana supercontinent that happened 200 million years ago. It's also a very beautiful cracked image. So it reminds me of the cracking of the Earth, the cracking of rocks, and the cracking of cells. It's a kind of cross-scale effect on the mechanical scale. So is it possible that the cross-scale effect of cracking could provide a new way of thinking to explore the plate formation experience? This is a thought that I started to have. I actually came across a big scientific question without realizing it. As we all know, the origin of plates is an unsolved problem in earth science until now. These two pieces of data, one is a recent U.S. strategic report, the other one is from China. Both of them regard the origin of plates as an unsolved problem in earth science. We all know that the world is divided into 6 major plates, although the theory of plate tectonics is almost a household word. But the earth science community has no good explanation for how plate movements are initiated. I used my own software to analyze the crack process. I simulated the internal expansion process of a ball. Let this internal expansion, as you can see, during the expansion process of this ball, in a relatively short period of time, a global scale rupture occurs. This is what I call the breakup of Earth today. This cracking process could be a good or reasonable explanation for the origin of the early Earth plates, a very good or a reasonable explanation. So finally, on July 16, 2020, Nature Communication published our results. Less than 10 days after it was published, about 23 international mainstream media, like ABC, Science Daily, etc., published 26 consecutive articles about this. Not only that, an international book called Encyclopedia of Geology also quickly included us in its plate tectonics section. Of course, this scientific exploration is still going on. Since the breakup of Earth can occur, what role did it play in the evolution of the Earth? Because it's not just a one-time cracking thing. Let's look at how the Earth has evolved over 4.56 billion years. You can see that during the 4.56 billion years of the Earth's existence, the Earth has had many ups and downs of hot and cold fluctuations. For example, the first one was the snowball event around 2.3 billion years ago. The entire Earth was almost surrounded by snow, including the vicinity of the equator. The second snowball event occurred between 600 million and 700 million years ago. Later on, the Ordovician Ice Age, the Devonian Ice Age, and so on. And now the Quaternary Ice Age. Many ups and downs with such big scales. The past Earth science of plate tectonics doesn't explain this very well. The mainstream extreme view is that the Earth itself is monotonically cooling. So why are there ice ages and thermal fluctuations? It's for other reasons. For example, carbon dioxide fluctuations, sunspot changes, even the change in the Earth's polar tilt, etc. Maybe these are possible considerations. But there is one thing that I think we can't avoid. Since the Earth can have a big crack, then this big crack must disturb the thermal fluctuations of the Earth. This is what I want to expand on today. I want to use common sense in life to explain to you what the thermodynamic system is. For example, if we go to eat hot pot, the waiter serves this pot of boiling water, which is the primitive heat. Of course, if we don't use fire to keep heating this primitive heat, we can't eat this hot pot. Why? The hot pot will definitely cool down. So let's light a fire. Of course, the fire must not be too big. It can't always keep the hot pot boiling. When the fire is not big enough, there is a possibility that although the fire is lighted and heat gets input, the system is still cooling down. We frequently encounter this situation when eating hot pot. So what do? Should we cover the pot with a lid? Note that you're not getting more heat with the lid on. It's still the same fire. So why does covering the lid work? It's because the lid prevents the heat from spreading. It doesn't increase the heat income, but it turns the system from a cooling system to a heating system. If we do an experiment, we put a pressure sensor inside and a temperature sensor inside, you will find that it will show a fluctuation of curve. Like, before you cover the lid, it cools down. After you cover the lid, it warms up and the temperature rises slowly. When it reaches a certain limit, the lid is pushed open. When the lid is open, there's a sudden drop in pressure and temperature, so it will rise slowly and fall quickly. Now let's go back to Earth. The Earth was a hot pot 4.56 billion years ago. The Earth was a sea of lava, so it must have cooled. So as it cooled, it formed a lithosphere. This process is the same as putting a lid on the Earth. After this lid is put on the pot, the heat inside, from the constantly exothermic phase, may enter a warming phase. So according to the theory of pot lid, we have made the reasoning clear. But let's look at science again. Let's look at the Earth system. Which kinds of heat are there? Firstly, solar energy input, which is the main concern. Secondly, the thermal changes between the Earth's mantle and its crust. Solidification and fusion will generate heat. The third is the most important heat source. There is an element inside the Earth called radioactive element. It has a half-life period of several billion years, and it is constantly producing heat. This heat is the fire of the hot pot I just mentioned. Of course, the Earth must be releasing heat. Whether it's covered or open, it keeps releasing heat. So there are 4 types of heat. I put these 4 kinds of heat, according to the thermodynamic equation, into a heat balance equation. Although this equation is very complicated, I just want you to understand 2 points. First, look at my equation. There is one item related to my breakup of Earth. Please look at this. L refers to the total length of the crack. If the Earth does break up quickly at a certain time, then this term dl/dt is a time derivative. It's an extreme value. When it becomes extreme, let's see, it also causes a sudden drop in temperature, like in the pressure cooker. The valve is open. What else drops? The pressure drops. So it will cause a drop in pressure. The pressure drop will cause a particularly important geological phenomenon. It's called decompression melting. Why? Because the melting point will drop due to the pressure drop. So we get 2 extreme conditions for this equation. First, the crack rapidly expands, the Earth will lose heat. This is obvious, like a pressure cooker will lose heat when it is open. There's another more important thing, which can't be expressed by a pressure cooker. That is, a sudden drop in pressure will result in decompression melting. What is the process of decompression melting? It's a heat absorption process. So this heat absorption causes the lithosphere to become essentially cold again. So that's one of my discoveries. The breakup of Earth is not just an act of crack. It may be the cause of the essential cooling of the Earth. So in this way, we can clearly see that the Earth's interior is heating up. Then the lithosphere is breaking up. The breaking up means releasing heat. The release of heat causes the Earth to cool. Remember, it's a conservation of energy. When it gets colder, the lithosphere repairs. The cracks, for example, will close. The heat is generated inside again. It's like a pressure cooker with a lid on it again. So my conclusion is that the Earth must have its own periodic pulsations. The whole evolution of the Earth is not necessarily driven by external factors only. There is a fluctuation inside it. Last month, I published this idea in the Science China. And in this perspective, I especially mentioned, since the heat has such a big fluctuation, then is it possible that major geological events are related to it? Hence I got a very important deduction. I think that the fluctuation of heat and cold inside the Earth will impact climate change on the surface. But the opposite is not true. What does it mean? Surface climate cannot in turn cause fluctuations in the evolution of the Earth. This is one of my basic ideas. So let's use this view to explain. The snowball event mentioned earlier. As you know, the Earth is surrounded by ice and snow. In the past, it was thought that, for example, the decreasing of carbon dioxide, or the reducing sunlight due to the changes of angle of the Earth, etc. These factors may exist. But there's another factor that I'm thinking about. Let's look at what happened to the Earth during the snowball event, which lasted for 200 million years. During this 200 million year period, firstly, there was almost no volcanic activity on Earth. Secondly, there was no orogenic movement. And thirdly, there was no magma activity. Even the drift of the plate slowed down considerably. This data is from an article in Nature. Since the Earth has been inactive for 200 million years, let's think about what is the cause and what is the effect. Was it climate change that caused the Earth to be inactive? Or is it the inactivity of the Earth itself that causes climate change? That's what I'm talking about today. And published in the Chinese Science Bulletin. I personally believe that breakup of the supercontinent. Because the breakup of the supercontinent is evidence, it's a fact. The breakup of the supercontinent before this snowball event caused the release of heat from the global interior. This heat release caused no lithospheric activity, no magma activity, no orogenic movement, etc. Of course, it also causes the temperature cools down on the Earth's surface. So it's a cause and effect relationship, not just for climate change. In my model today, changes in the Earth's interior don't just affect the climate. They also reshape the surface of the Earth because they're so powerful. The Grand Canyon of Colorado, for example, we used to think that it was created by water. Of course, water is powerful, I'm not against that. But the Grand Canyon of Colorado, you can check it out. 1,500 meters, 1,600 meters depth of this kind of wall is definitely not scoured by river. So actually, when you go to see it, scientists have several questions on the table. The first problem is that the Grand Canyon of Colorado, why is the top of the valley 1,000 meters higher than the upper reaches? The second question is, why did the Colorado Grand Canyon form in a much shorter time than geologists have predicted? Because it takes a long time for rivers to scour. There is a third question, which is more interesting. Why didn't the river scouring from the Colorado Grand Canyon form a large delta? Because if you go to Google Earth and look it up online, the Colorado Delta is not among the top 10 deltas in the world. But the Colorado River is considered that. All the rivers in the world can't fill half of it. So where is the dirt washed out by the river? That's my question. I will explain it with the theory of cracking. As you know, cracking is an act of cracking under tension. There are two types of cracking in the form of trigeminal cracking. The first one is when three cracks are created almost simultaneously. It is 120 degrees intersecting. But if it has a main rift valley, then when it creates a secondary rift, it intersects at 90 degrees. While just in the Grand Canyon of Colorado, you can look it up on Google Earth, along the main canyon, which is over 400 kilometers long. There are a lot of vertical bifurcations, and for your information, these vertical bifurcations don't even have water. It's barely a river. So I think that the Grand Canyon of Colorado must be caused by mechanical rifting behavior. So I published this idea in the Chinese Science Bulletin. I came up with my own theory of stress rifting. I think the uplift caused the cracking. So is there any evidence for uplift? Yes, there is. The Colorado Grand Canyon is a plateau. This plateau started uplifting 70 million years ago. There have been about 3 major uplifts. The total uplift height is about 3.2 kilometers. So each uplift, according to what I learned in mechanics, its curved uplift must have caused a rift. So the rift is divided into several times. The real breakthrough came in about 5 million years. Because it is uplifted, it is reasonable that the valley top is higher than the upstream. Then what is the second reason? Why does it form in such a short period of time? Because as I said earlier, it's not washed out by water, not slowly. It's a rift formed by a large earthquake. Then why is there no big delta? Because it's not washed out, it's an uplifting and cracking behavior. So it has a delta, but it's not the biggest. These are the two explanations I have today. These explanations can be extended to, I think, the Yurlungzhangbo Grand Canyon in China. I think the Great Rift Valley and the Baikal Rift Valley. We can find their formation mechanism from uplifting and cracking. Scientific exploration is, of course, to make bold hypotheses and seek proof carefully. So I've summarized about the results of my research over the years by using this diagram. Look at the horizontal bar in the middle of the diagram. It represents 4.56 billion years. The color of the bar represents the change in temperature during the 4.56 billion years. Yellow is the highest temperature. Red is also very high and must be uninhabitable. The white areas are the ice ages. There are fluctuation curves on it. I've put a lot of major geological events on this graph. For example, the snowball event, the great oxygenation event, and the biological extinction event. I found that during the most active times of these major events, they were all in the high temperature periods on this graph. The quietest times are during the low temperature periods on this graph. That's why this graph was introduced by the Foundation's recent Chinese Journal of Strategy Studies. This is about the Earth. So we can think about this question. What is related to so many geological activities on the Earth? This is a key point I made. The thermal fluctuations in the Earth's interior. It could be a homologous driven of major geological events. Many events are related. It's the same system. We'll explain it more to assist understanding of the Earth system. Let's think about our planetary system, at least those Earth-like planets. Since the Earth has been able to produce these fluctuations for 4.56 billion years, then how about the other planets at the beginning of their existence? We know that Mars and Venus are twin sisters, right? Why did Mars get colder as it went along? Venus got hotter as it went along? I actually think it's possible that they're both at different stages in their history. They have cold times and they have hot times. For example, if the Earth has this fluctuation, do other planets have it? I think they do. Of course, the size and frequency of these fluctuations are different. Because the size of the ball is different, the distance from the sun is different, and so on. There are different fluctuations. But as time goes by, you see, at any given moment, look at its state at that time. Look at the first one. There is high temperature, medium temperature, low temperature, right? Okay, so the next moment, it's the same. The high temperature becomes low, and the low temperature becomes high. So it's constantly fluctuating. So don't take it that the cold Mars today will be this cold in the future. And don't take it that the hot Venus today will be this hot in the future. Let's look at the evolutionary history of the Earth. In short, the Earth has been around for 4.56 billion years. It has survived 5 major biological extinctions, and due to there were no Homo sapiens. So these extinctions were all natural extinctions, right? So scientists tell us that our planet has 4 billion years left. Then the future of the Earth is definitely not doomed, right? The snowball, ice age, all these times. We can't just make it quiet just because there are humans today. We don't have that kind of power. Humans will only use our intelligence to meet the future with its unrest and its turmoil. The 6th mass extinction will surely come. But there are humans and Homo sapiens. Can we humans use our intelligence to meet the challenge of future planetary catastrophes? That's the question we have to think about. Well, as people on the Earth, as human beings, we should consider the problems of the Earth on a global scale, on a million-year scale, and pay attention to the past, nowadays, and future of the Earth on which we live. Thank you.